Good afternoon, everybody. How are you? That's good. My name's Peter Ashman. I'm an Associate Professor in the School of Chemical Engineering. Thanks, Louise. And I wanted to talk to you today about this grandiose topic, how chemical engineers change the world. Now, I'm obviously a chemical engineer. I've been a chemical engineer now for 20 years, I guess, and I still remember the time that I was sitting not exactly where you guys are, but in a similar situation. I guess a lot of you are approaching the end of your high school days and wondering what to do with yourselves. And I ended up doing chemical engineering pretty much out of a fluke. I guess it could have all gone horribly wrong for me, but I ended up finding a career that I love, and I'm very happy that things turned out well for me. So I want to talk to you about a little bit about the history of chemical engineering and how I think chemical engineers have in fact changed the world. I want to talk to you a little bit about some of the things we're doing here at the University of Adelaide now, trying to change the world of the future. And then right at the end, we might look at some of the really big challenges that I think you guys will help solve. They'll be solved well past the time that I'm retired, I'm sure. So, a bit of an interactive session. So, chemical engineering, let's get into some chemistry, I guess. Does anyone recognise this particular molecule? You can have a guess. And start picking on people. This guy down here in the Everlast t-shirt. No, it's you. Have a guess. What do you think that might be? No idea? This guy up in the back with the beanie. Sing out. What is it? No idea. Anyone? Okay. This particular molecule is called penicillin. Okay? Penicillin. And this little molecule has changed the world. Okay? Before we had penicillin, tiny injuries, like the first patient that was treated with penicillin scratched his face in the garden on a rose thorn, and he had such bad infections on his face that they had to actually remove his eye as part of the treatment. And they actually treated him with the very first dose of penicillin, and he showed some improvement, but unfortunately they didn't have enough penicillin to treat him properly, and that guy actually died. But these days we treat minor infections, we don't even worry about them because we've got modern drugs that we can use to treat them. But in the old days, people died from such infections. So penicillin changed the world. Does anyone know who invented penicillin? Who's recognised as inventing penicillin? Come on, some of the mums and dads know this one. Who's this guy? This is not Florey. This is actually Fleming. So Fleming is the guy who actually discovered penicillin. And in fact, Florey, who we've given the unusual honour of being on our old $50 notes, Florey was actually the guy who demonstrated how it could be used in medical practice. And both Fleming and Florey and some other guys who we always forget about, they actually went on and won the Nobel Prize in 1945. Now Florey we always talk about here at the University of Adelaide because, of course, he studied here. He did his medical degree at the University of Adelaide. And in fact, recently the university in sort of its bold vision looking forward, the Beacon of Enlightenment actually looks at some of the early days of the University of Adelaide and honours some of these early founders and early pioneers of science and engineering. So as I said, these guys won the Nobel Prize for Medicine in 1945. Now these guys, yes, they changed the world, but they invented something that I think would have been a scientific curiosity or perhaps at best a sort of boutique treatment for the rich, but it was actually chemical engineers who turned that invention into a practical product that was used for great benefit right throughout the world. Now, penicillin, as I said, was able to cure some interesting diseases. There's one, but of course, when penicillin was invented, there was a real need. Penicillin was invented just before the Second World War, and by about the middle of the Second World War there were hundreds of thousands of people dying, and many of those deaths were not necessarily due to wounds. They didn't die on the battlefield, they actually died later on due to the infections that they received from their wounds. And so developing large-scale production of penicillin became one of the highest priorities of wartime science and engineering. So that was in World War II. So at the time, the production method for penicillin was to grow them in these little flasks that you can see here. And in chemical engineering, we talk about scale up. So we talk about how we can take a process that happens at very small scale and make it happen at very, very large scale. And these guys weren't engineers, they were scientists and doctors, and so for them, scale up was, instead of doing it in one flask, they would do it in 50 flasks. And it's a form of scale up, but it's not very efficient and not very practical. These are the guys, or some of the guys that actually were involved in this technological breakthrough of producing penicillin at large scale. So there's a guy called Jasper Kane at the top, and John McKean. And John McKean was a chemical engineer. He was a US chemical engineer working for a company called Pfizer. And they were given, while much of the research on penicillin was done in the UK, at the time they were really struggling through the Second World War, and they didn't have the resources to put into this large-scale production. So they essentially handed over their research to the US scientists and engineers, and Pfizer was one of several companies who took up the challenge. And Pfizer had actually made a name for themselves producing a product called citric acid, which interestingly they'd got into during the First World War, because the process for producing citric acid until that time had been via lemons and limes, and at the time they actually imported those from Italy. And during the First World War, that supply was cut off, and so they had to find another way of producing citric acid, and so they were actually fermenting organisms and then using those organisms to produce the citric acid. And they used a process called surface fermentation. And that's what they first tried to use in the large-scale production of penicillin, and they were partially successful in using that technology. But it really lacked something that they needed. It was very unreliable, and it just didn't really work properly. And so the guys at Pfizer really beat themselves up for a while to try and come up with something different. And eventually they turned to, would you believe, brewing. There was a process used in the production of beer called deep fermentation, deep tank fermentation. And they were actually able to successfully apply that technology in this new area to produce penicillin. And they were extremely successful. So they worked around the clock. They were working 16 hours a day, 7 days a week in the sort of 1942, 1943 to scale up penicillin production. They were astoundingly successful. They set themselves a target of achieving this within 6 months, and they're actually able to do it in less than 4 months. So to go from a lab scale process to a full scale process, these days we might talk about years, maybe 5 years, maybe 10 years. These guys did it in less than 4 months, which is astounding. They were so successful that within 9 months they'd actually produced 45 million units of penicillin. And that led to the fact that on the D-Day invasion of France on 6th of June 1944, every Allied soldier carried a dose of penicillin in his kit, and 90% of those doses of penicillin were produced by Kane and McKean at Pfizer. So from this little story, chemical engineers make science useful. Okay, I hope I've passed that on. So while scientists do great work, it's the engineers that take that great work and turn it into something that is actually useful for society. Chemical engineers also deal with huge risks, and I wanted to just briefly touch on some of this in a minute. And chemical engineers can make or break companies. When you go back and look at this decision that Pfizer made during the war, they did it for reasons of patriotism, but they also did it as a business investment, and it was an extremely risky investment, but one that paid through in the end. But it could have all gone horribly wrong for them. So this is what chemical engineers do. But what do they really do? That's just one example. Well, I'd like to say that chemical engineers change raw materials into valuable products. And that's really what we do. Sometimes we use chemical processes, sometimes we use physical processes, sometimes, as in the case of penicillin, we use biological processes or mixtures of the three. There are two pictures here. One is a raw material. So this is a picture I actually took at the Michelle's Wool Washery out near Salisbury on Main North Road. And they have quite an unusual process. They've got quite a few chemical engineers working out there. And they take dirty, stinky, smelly wool from sheep, and they essentially wash it. And it's quite a complicated process. They actually produce some very advanced textiles and lots of chemical engineering involved in that. On the right-hand side here is some very valuable product. This is the Penfolds Red Wine Store in the Barossa Valley. So I can't imagine how many dollars worth of red wine are sitting there in that particular photo. So that's what chemical engineers do. We turn raw materials into valuable products, but we have to do it in a special way. We have to do it, first of all, we have to do it safely. And that's often the first criteria that we apply. We also have to do it economically. We have to be making money out of this particular venture of turning raw materials into valuable products. And we also have to do it these days, we have to do it sustainably. Okay? And sustainability is a complex concept, and I don't have time to go through it today, but I guess the sort of simple version of sustainability is that we have to do it environmentally, in an environmentally sound way. Okay, so I mentioned something there about safety, and I said chemical engineers have to deal with huge risks. One of the topics that we deal with in chemical engineering is called process safety. So when we're working on these processes for turning raw materials into valuable products, we have to do it. Sometimes we're working with processes that are intrinsically very dangerous, and we have to find ways of making those risks acceptable. And so there have been many hard lessons learnt in chemical engineering. So in 1988, the mums and dads might remember an incident that happened in the UK, fire on an offshore oil rig. 167 people died in that incident, and it was really the following on from that incident that modern day chemical engineering process safety evolved, and people started to work really hard to figure out how we could stop this from happening again, or with less severe consequences. Unfortunately, despite our best efforts, occasionally things continue to go wrong. So in 1998, closer to home, there was an incident at the Esso Longford plant. 2 died and 8 injured. And then, I'm sure you'll all remember, only a few years ago, the Deepwater Horizon incident. Probably best remembered for the massive offshore oil spill and the multi-billion-dollar damages claims that are going on at the moment. And people often forget about the 11 people that actually died on that particular day. And what's different about process safety is that we can think about safety in terms of this particular spectrum where we have, on this scale, we have frequency of incidents. So down here we've got things that are happening quite frequently, so maybe 100 times per year, but they've got quite low consequences. So, we might be talking about slips and trips, people sprain their ankle or cut their finger. And most organisations, this is the end of the spectrum they're dealing with. Things that happen quite frequently, sorry, record now. And then up here is where chemical engineers are working, where we've got incidents that are occurring much less frequently, but with much more severe consequences. And so through the actions of chemical engineers, what we're trying to do obviously is decrease the severity of incidents, so when things do go wrong that the consequences are less severe, and obviously reducing the frequency of those incidents. But it's the fact that chemical engineers are dealing with these low probability, high consequence events that makes what we deal with in chemical engineering so much different from what most organisations think of when they talk about safety. So for chemical engineers, safety, we're much more concerned with this end of the spectrum than down at this end. Okay. Now I wanted to talk a little bit about some of the work that's happening today at the University of Adelaide. And I'm involved in a range of activities at the university on the research end, and one of the things I'm interested in is how do we use biomass and biofuels more productively. So I want to go through this reasonably quickly. I'm conscious of time here. So biomass is here. We've got pictures of biomass. It's really any material that's been derived from plants, and biofuels therefore are fuels that are effectively derived from biomass. There's a whole bunch of examples of different biomass and different biofuels that you might think of, and I've got a few examples here. But I wanted to go on and talk in a little bit more detail in a moment about this particular one, aquatic plants and algae, because there are some real advantages for using these types of materials for biomass. In terms of biofuels, these are the sorts of things that we normally think about. So we can have biofuels which are solid fuels, and in fact the gas is today the most widely used biofuel in Australia. The gas is a byproduct from the sugarcane industry, and they burn large amounts of this material up in Queensland to provide the energy for that sugar making process. A fair amount of wood waste is used in Australia. I'm sure you've all heard about ethanol and bioethanol that goes into petrol that we put into our cars. Biodiesel is another liquid transport fuel that's used quite extensively in Europe and to some extent in Australia. And then there are some quite common gaseous biofuels. A lot of dumps these days produce landfill gas, and in fact biogas is a common product from waste treatment processes like at Bolivar, the wastewater treatment plant at Bolivar. They have quite a big biogas generator out there. So bioenergy's got a lot of good things going for it and some things going against it. So I've shown here in the green some of the things going for it. Lots of demand for energy these days, and so you know, if you're working in bioenergy, you can be sure that there will always be a demand for your product. Biofuels is seen as a way of mitigating CO2, so greenhouse gases, and so there are certainly political drivers that are making, you know, forcing these sorts of behaviours, and maybe in the future we might also have some economic drivers to force CO2 abatement. And then there's these other ones here, so reducing CO2 emissions due to fuel substitution. People are concerned about energy security, and so having locally produced bioenergy is a way of dealing with that. Bioenergy is often done in regional areas and leads to employment, so these are other drivers for bioenergy. There are environmental benefits in some cases, and then there is waste recovery and synergistic benefits. So often biomass and bioenergy occurs where there are other things going on. So for example, in Western Australia, they plant a lot of mallee trees as a way of reducing dryland salinity, and then there's a bioenergy benefit from that as well. But there are some things going against bioenergy, and I guess the main one that people think of is the fact that if we're growing plants for energy, then we're directly competing with food. And when we live on a planet where a very large proportion of the people on the planet can't grow enough food to feed themselves, some people are uncomfortable that in developed countries we want to start growing food for energy. At the moment, the production of bioenergy is not particularly economical, and it needs either large subsidies or a very large penalty on the price of carbon to make it cost effective. And then there are some other negative issues as well. Now, some of these, so we can think of biofuels in terms of this carbon life cycle, and people think that, or people consider biofuels as a carbon neutral way of producing energy. When we burn the fuel, we produce carbon dioxide. When we grow the plants take up that carbon dioxide, and then that gets released again. And so there's this cycle of carbon neutrality. And so people say biofuels are carbon neutral. But I think that's a statement that needs to be qualified. And in some cases, biofuels are carbon neutral. In some cases, they're not. So here's some data that comes from the literature. And it shows the life cycle CO2 emissions from certain types of fuels. And here for a reference is conventional diesel that we put in our cars. And so if we say that it has a relative CO2 emission of 1, we can see that biodiesel produced from canola, which is probably the most common source of biodiesel in the world today, has a relative CO2 emissions of only half of that of diesel. Okay, so not 0. People say, oh, well, biofuels, it must be carbon neutral. If it was carbon neutral, that number would be 0. But it's not, it's 0.5. And that's because there's a lot of energy that goes into producing, growing the canola and then converting the canola into biodiesel. You can make carbon neutral biofuels, and a good example is if you use waste cooking oil. Okay, so you go into your local McDonald's or KFC and you get some of the oil they've been using to cook their chips in, and if you convert that to biodiesel, you end up with a product which is approaching carbon neutrality. The problem with that is that despite our love for McDonald's and KFC, there's not a lot of that waste cooking oil floating around, and so you can't produce a lot of that at large scale. Here is a type of biofuel that we're interested in at the University of Adelaide, and it's this algal biodiesel, or using algae as a biofuel. And if you do the same sorts of analysis, you can see that potentially, when you're growing algae, you can produce something which is much better in terms of greenhouse gas emissions than canola. Interestingly, with some biofuels, you can actually do a lot worse. So people have done studies and looked at biodiesel being produced from palm oil, and particularly if that palm oil is coming from plantations in Southeast Asia that used to be natural rainforest. By the time you take into account the increase in greenhouse gas emissions due to the land clearing that occurred when those rainforests were cleared, you can end up with a biofuel which actually has 6 times the CO2 emissions of conventional diesel fuel. And so this is why people get annoyed about wide-scale subsidies for biofuels, because in some cases that can be a very good thing. In some cases it can actually be a very bad thing. It's in fact quite a stupid thing to do. So, and so this is a little cartoon, I think, which just emphasises that point that I was making before about people being uncomfortable about growing crops for fuel when there are people who are in the world who are starving. So we think that microalgal biofuels is one way of avoiding some of these problems while still leading to some of the advantages that we've been talking about. So the reason people are quite excited about microalgae is from data like this. And if you look at, say, canola oil, which is here, and if you calculate based on the yield that you can get per hectare for canola, if you go off and calculate how much land you would need to plant with canola to meet the US transport needs. So here is the land area for different biomass feedstock. In fact, this is to meet 50% of the US transport fuel demand. You would have to actually crop more, so 122%. So more than the currently available arable land in the US would need to be planted in canola to actually meet half of the current transport fuel demand. So that says you're never going to be able to replace transport fuel using biodiesel from something like canola. But with microalgae, and depending on some assumptions that you make, you can actually meet those demands with a very small amount of land. Maybe 1% or 2% of the US arable land could be devoted to microalgae, and you'd be able to meet a large part of the US transport fuel. But the good thing about algae is there's some types of algae you actually don't even need arable land. You can actually plant it on non-arable land. So you're not actually directly competing with food crops in that sense. So at the University of Adelaide, we do small-scale culturing of microalgae. We grow it in small scale in the lab. We also grow it at slightly larger scale outdoors. So this is some tanks that we had sitting on the top of the Mawson building at the University of Adelaide here. But we've also gone to much larger scale. So we've been growing microalgae at a place called Karratha on the northwest of Western Australia. And there's lots of reasons why we chose Karratha as a site. One of those is that we were collaborating with a group based in Perth, and they had some good contacts in Karratha. And so we built a pilot plant over there, and this is the picture of our pilot plant. And this much bigger site over here is a gas-fired power station owned by Rio Tinto. And so this land belonged to Rio Tinto. They let us use some of their land to grow the algae. And here are some of the ponds that we're growing the algae in. So these were 200 square metre ponds. You can see the scale here, person standing in front. And we were growing about 60 kilos a day of microalgae on this pilot plant in Karratha, very successfully. And we were able to, there's more pictures of the pilot plant, we were able to process that algae through harvesting, large-scale harvesting. Here's the first, sorry, there's one more picture, oh no. Sorry, I'm missing a picture there. So this is our processing of the algae, harvesting from at large scale, and this is our first bag of algae that we froze and then sent back to Adelaide for us to do some more work on. We're also obviously interested in how we do conversions of the fuel. So without going into the details, these are processes that we use to convert the biomass, the solid algae, into fuels that we can use in our car. And here is some oil produced from algae. We've actually closed down that site in Karratha. It's achieved what we wanted to achieve, and we've now begun work to build a much larger plant in Whyalla. And we've actually commercialised, or in the process of commercialising this. We've set up a company called Muradel, and they will go on and build a much larger pilot plant based in Whyalla. Okay, so that's some stuff that we're doing here, that we have been doing here at the University of Adelaide. I said I'd talk to you about some challenges for you guys when you become chemical engineers. So there are the US Academy of Engineering, have listed what they see as the 14 grand challenges for engineering. And some of these are very relevant for chemical engineers. This is one that we're actually working on as well at the University of Adelaide now, in the Centre for Energy Technology that I'm part of. We actually work on a technology called solar thermal energy, and one of the key challenges there is making that more affordable. Providing energy from fusion, okay, not something that we're working directly on here at the university, as far as I'm aware, but certainly around the world, people are very keen on being able to make fusion work at practical scales. Carbon sequestration methods, so again, this is something that a lot of people at the university here and around the world are working on. Ways of capturing the carbon that we might produce by burning fossil fuels and putting that into places where it will be stored stably for long periods of time. We talk about the carbon cycle and carbon emissions, but there's also a natural nitrogen cycle that human activity is disturbing quite dramatically, and I think over the next 10 to 20 years you're going to start hearing more about this natural nitrogen cycle and the effects of man on it. And then there are a whole bunch of other challenges: access to clean water, urban infrastructure, health informatics, better medicines, reverse engineering the brain, preventing nuclear terror, securing cyberspace, enhancing virtual reality, advanced personalised learning, and engineer the tools of scientific discovery. So obviously some of those first few chemical engineers are very much going to be involved with. Some of the later ones probably, but certainly there'll be other engineering disciplines that'll be leading those challenges as well. So I guess that's my little story about chemical engineering and how it's changed the world. I guess I have to finish off quickly with a bit of a pitch. So for chemical engineers, on average there is strong demand for workers in this area. We do see cyclical demand, so some years are better than others, but on average over the long term there is strong demand, and that's because there is recognised that there is definitely skills shortages in these areas, and the fact that there's more engineers retiring than we're actually training. So this is a balance that we as a country need to address over the years. The good news is that if you're studying engineering now, it means that there's very likely that there'll be a job for you in the short to medium term and the longer term. Chemical engineers get paid very well, so we typically come out on the top of starting salary league tables. We also are one of the few engineering disciplines that do very well at attracting females, girls into the discipline, and that's obviously good for the discipline to have a well-balanced pool of human capital. We also, as chemical engineers, we are often working at the cutting edge of science and technology. Chemical engineers say that we work at the edge of the boundaries between the disciplines. So we work at where science meets engineering. And just to name some areas that we work on at the University of Adelaide, so these are all sort of strong research areas in our school: nanomaterials, pharmaceutical engineering, bioengineering and biotechnology, clean energy and sustainable engineering, and microfluidics. So these are just some examples of some cutting-edge science and technology that we work on here. As engineering graduates, there is, as I said, strong international and domestic opportunities. If you're interested in travelling the world, I know many of my former students have gone on to spend a lot of time working internationally. Of course, if that's not what you want to do, then there are plenty of domestic opportunities as well. And I think if I finish up by saying that, you know, I found it to be a very rewarding profession, and it's definitely a profession where you can actually and feel like you're making a strong difference. So I think I'll leave it there and open the floor if we have any questions. Any questions before we... Yes? If you study high-level maths at Year 12, where does it lead to? Well, so I think for all of the engineering disciplines, mathematics is a key enabling skill. And so I think if you're doing Year 11 and 12 and you're doing some maths and you're hating it, then I'd maybe suggest that you might think about something other than engineering. If you love maths, then engineering is the place to be.